the magnetizing reactance, and this is the rotor circuit. Now from this figure, the current I1 drawn by the motor will be this current flowing in the shunt branch or the no load current plus the current flowing in the short circuited rotor circuit. So approximately from here we can get that the current is given by, here I have written I2, that I1, it will be I1. I1 is given by supply voltage divided by the total impedance of the circuit. Now, here actually you can see that approximately that negative this current has been shown. Now, at starting condition, at starting, S is equal to 1, the slip is 1. So starting current will be V divided by root over of R1 plus R2 square plus X1 plus X2 square. So power factor at starting will be it is a short circuited circuit, so this is the total resistance R1 plus R2, S is 1, and X1 plus X2 is the reactance. This branch has been neglected in this expression because that current is small compared to the other one. So power factor will be R1 plus R2 divided by root over of R1 plus R2 square plus X1 plus X2 square. So T starting is this is the synchronous 1 by synchronous speed. So I2 square R2. It is proportional to the so approximately if we can neglect this branch or if we shift this parallel branch to input side, so approximate circuit if we take, then it is seen that the torque is approximately proportional to the copper loss I2 square R2 in the rotor circuit and can be increased to the maximum torque of the motor by increasing the resistance of the rotor circuit that we have seen earlier while deriving the torque expression. But however, if it is a slip-ring motor, then only we can change the rotor resistance, otherwise not. For starting the motor, Y-connected resistance are connected to the slip rings. In case of slip ring motors, during starting, this external resistance is set to its maximum value, and then gradually, once the motor started, we reduce the resistance. Now, in case of slip ring motor, if these resistances are designed to carry the full load current continuously, then this can be used for speed control also, these resistances. Otherwise, if these resistances are only used for starting, then these are for short time rating. And if it is used continuously, the temperature rise will be very high. So the expression, approximate expression of torque is this, is square is the number of phases here. So R2 by S, R2 plus R1 plus R2 by S square, X1 plus X2 square. So therefore, if R2 dash is inserted in the circuit, it is made such that R2, if inserting the resistance, if it can be made that we can have the maximum torque as starting, that we have derived earlier, because that sleep at maximum torque occurs, that is approximately proportional to the resistance of the rotor circuit. However, in case of squirrel cage motor, we cannot control the rotor circuit resistance. But in case of squirrel cage motor, what is done when we go for the construction, you will see that we have deep bar rotors, that is the length of the rotor slot is quite high. Now at starting, what happens, the frequency is F, the supply frequency. So the inductance effect will be quite high, and that makes the current distribution uneven. The current will tend to flow through the low impedance path. So current flows to tends through the through the outer portion of the conductor, so that the inductance is less. So that becomes, the current distribution becomes uneven. So the effective conductor area reduces, increasing the resistance. But as the speed increases, the slip decreases, so the rotor frequency decreases, so the current distribution becomes even. And under normal conditions, slip is very small, so rotor frequency is very low, so current distribution is almost uniformly distributed, so the effective resistance decreases. So that is how, with deep bar rotor or double cage rotor for squirrel cage motor, we get sufficient large starting torques. That we will discuss during the construction. Now, what we can do, we can have direct online starting. This is very common method. Small motors, even medium or high voltage motors, can be connected direct online, depending on other loads connected to the system. Small motors are always connected, started direct online. The motor draws a large starting current at low power factor. At starting, the main current, a very large portion of it will be the magnetizing current. So power factor is low, and the magnitude is something 5 to 7 times the full load current. Large starting current does not harm the rugged squirrel cage induction motor, but cause objectionable voltage drop in the line. This large voltage dip might be momentary, but it adversely affects the other loads connected to the line. So for medium and high voltage motor, if the line capacity is sufficient, then those motors also can be started direct online. Now here we can take the ratio of starting torque and full load torque. So approximately we have seen that the torque is proportional to I2 square R2. So R2 by S. So starting torque is proportional to I2 square R2, because S is 1, and full load torque is I2 full load square R2 by S full load. So is starting by T full load. Sorry. So yeah, starting torque to full load torque ratio is approximately equal to starting current to full load current square. Ratio of starting current full load current square into full load slip. If the no load current is neglected, if this expression all the expression, no load currents had been neglected. The approximate expression. So I starting by I full load is equal to effective rotor to stator turns ratio by effective to stator turns transition into I2 starting by I2 full load. This I starting by I full load, it's the stator current. So this was the rotor current. So in both the cases, if we multiply by the effective turns ratio, so approximately this can be taken as I starting by I full load is equal to I2 starting by I2 full load. This obviously we are neglecting the shunt branch current. So our actual expression was T starting by T full load, I2 starting by I2 full load square into S full load. This is approximately I starting by I full load square into S full load. Now, if Z1 is the standstill per phase leakage impedance referred to the stator, then the per phase short circuit current at standstill is given by short circuit current is defined by the voltage divided by the short circuit impedance. For induction motor, short circuit impedance is the standstill impedance, that is taking S is equal to 1. So for direct switching, I starting is equal to I short circuit is equal to V by Z1. So we can write for direct online switching, I starting by T starting by T full load is I short circuit by I full load square into S full load. Now, obviously, the current will be high, starting current will be high. One of the method of reducing the starting current is reducing the voltage. So we have reduced voltage starting. So simplest one is the stator resistance or reactor starting. That is, we can insert a resistance or reactor in series with the stator winding in each phase, so that a voltage, a part of the voltage is dropped across the reactor or resistor. Here reactor has been shown, it can be resistor also, but normally for induction motor we go for reactor because resistor will cause additional loss, I square loss. However, in some circuit it might require resistor starting because reactor starting increases the reactance and makes the time constant larger. So here, say a part of the voltage is dropped across the reactor. So say a part XV is appearing here. So if V is the per phase voltage, then the line to line is √3V. So here, what is appearing across the motor terminal is √3XV. Now, so I starting will be applied voltage divided by the short circuit impedance. So applied voltage is XV, per phase voltage. The line to line is √3XV. So per phase voltage is XV by per phase short circuit impedance Z1. So this will be X I short circuit, because I short circuit is defined as V by Z1. So T starting by T full load will be I starting by I full load square into S full load will be equal to XS square I short circuit by I full load square into S full load. So here you can see that the starting current reduces. Similarly, the torque also will reduce by this factor XS square. The induction motor torque is approximately proportional to the voltage. So the torque will also reduce as we have reduced the voltages. So the starting torque to with reactor starting torque to direct switching will be, the ratio will be x square. Now, very widely used for the induction motor for starting is the auto transformer starting. So here in this figure you can see that this is a auto transformer, three-phase auto transformer star connected, and the motor stator is also star connected. So the stator is supplied from the output of the auto transformer, which is variable. This point is variable and vary from 0 to the full rated voltage 3V. So if supply voltage is V, then a fraction of the supply voltage XV is appearing across the stator terminal. So this will reduce the static current. After the motor has accelerated, the auto transformer can be disconnected, or normally we can what we do, we make vary this point to the full voltage. So full voltage is applied. So per phase starting current for the motor will be the motor current flowing here will be XV, the applied voltage, divided by the standstill impedance Z1. So this will be again X I short circuit, where V by Z1 is the I short circuit. If the transformer no load current is neglected, then the per phase VA input VA is equal to per phase output VA. So actually this current, the more flowing in the motor stator terminal, but what is drawn from the supply is this current. Say this is I starting. So input VA will be I starting into V. So that is equal to voltage applied to the motor winding into current drawn by the motor winding. The voltage applied to the motor winding is XV. Current drawn is X into I short circuit. So I starting is here equal to X square I short circuit. So you see that in case of reactor starting, it was X I short circuit. Here, when we are using auto transformer, it will be X square I short circuit. So the current drawn from the supply is reduced by X square times the current drawn by the motor during the direct switching. So the torque, T starting and T full load ratio of these two torque will be per phase starting current in motor winding by per phase full load current drawn by the motor winding into, there will be a square of that into S full load is equal to X I short circuit. This is the per phase current drawn by during starting by I full load square into S full load. So X square I short circuit by I full load square into S full load. So T starting by T full load is equal to X square I short circuit I full load square by I full load square into S full load slip full load slip. So this is this I short circuit. From here it is 1 by X square into I starting, that is the current drawn from the supply. So substituting that by 1 by X square I starting into I full load divided by I full load, the whole of this square, it will be this will be 1 by X to the power 4. So the 1 X square will cancel out. So it becomes 1 by X square I starting by I full load square into full load slip. So our ratio of starting torque to full load torque will be X square. Here this again this I starting is replaced by this X square I short circuit. So X square I short circuit this is basically I starting square. So one is replaced by I square xx square I short circuit into I short. So this will be equal to I starting in, this is I starting into I short circuit by I full load square into S full load. So part phase motor starting current in terms of I starting is given by X I short circuit is equal to X into 1 by X square I starting equal to 1 by X I starting. This is the current drawn from the supply. So in a induction motor, torque is proportional to the voltage square. So starting torque with auto-transformer by starting torque with direct switching will be equal to xv by v square. So it will be x square. With auto-transformer starting, the starting current from the main and starting torque are reduced x square times their corresponding value with DOL starter. Another possible connection is star delta starter. This is obviously if the normal connection is delta, then we can go for this starter. That is initially the this is the circuit that is it is a double throw switch. So initially it is connected on this side. So these 3 points will be shorted. So the so the windings will be connected in star. Once the motor has started, this will open and connect on this side. If it is connected on this side, then the windings will be connected in delta. So normal running condition, the motor will operate in delta connection. Now, what is the advantage? The per phase motor starting current is given by we are connected in stars. So if the V is the supply line voltage, then the phase voltage will be V by root 3 by Z1. So this is the starting line current in star connection. So when the stator winding connected in star, I starting Y is also the starting line current. If the stator winding is delta connected, then for direct switching, the per phase motor starting current will be, if it is connected in delta, then the delta winding per phase current will be I starting delta will be supply voltage V by Z1. So V by Z1 is the short circuit current, I short circuit delta. And I circuit star, you can see where it is 1 by root 3 times this value. So starting line current for direct switching will be, now this current is the phase current for delta connection. So actually current which is drawn from the supply is the line value. So it will be root 3 times this. So the current drawn from the supply will be root 3 times V by Z1 or root 3 I starting delta. So equal to root 3 I short circuit delta. So this is the value of the current which if the machine will drawn if connected in delta, and this is the current it is drawing when it is connected in star. So starting line current with star delta starter by the starting line current with direct switching in delta will be I starting star divided by root 3 I starting delta, because this is a line current. This is for star line current is equal to phase current. For delta it is root 3 times the phase current. So this will be 1 by 3. The ratio will be 1 by 3. So starting torque starting torque with direct switching in delta, the ratio will be the torque is proportional to voltage square. So here for star delta per phase star connection per phase voltage is V by root 3. So this is V by root 3 square divided by V square. For delta the voltage is V. So the ratio is 1/3. So it is seen that if an auto transformer started X is equal to 1 by root 3, then the starting current and the starting torque are reduced to 1/3 of their corresponding values for direct switching. So with the delta starter, the motor behaves as if it is started with an auto transformer with ratio 1 by root 3. Starting torque with star delta starter by full load torque with stator connected in delta will be current square into R2 by 1. Here also current square into R2 by S full load. This is the full load current. So it will be I star delta star. This is starting delta start. So I starting delta by root 3 square by I full load delta square. So it will be 1 by 3 I starting delta by I full load delta square is full. So an auto transformer starter is now an auto transformer starter is costlier than the star delta starter because a total separate unit of auto transformer is required. So star delta starter is used extensively, but it can be only used if the normal connection is delta. Then we will go for the star delta starter. Otherwise, we have to go for the auto transformer starter. However, above 3.3 kV motors are normally star connected as delta connection is expensive. So then we cannot go for star delta starter. We have to go for auto transformer starter. Now for line start motor, that is directly online start, the motor which is directly online started. Generally, we can have 3 types depending on the motor parameter. That is high resistance rotor, high reactance rotor, and double squirrel cage rotor. Resistance and reactance of the motor depend on the size and shape of the rotor slot. As I told, we will discuss it during the construction in details. So whether the motor is designed with high resistance or high reactance, that are design parameters. Now the advantage and disadvantage is that the high resistance rotor gives a large starting torque at a good power factor because of the high resistance. The full load slip is large and efficient, but efficiency will be poor. This can be related, derived from the expression we have derived. That is, if we have large rotor resistance, the starting torque will be large. Power factor will be better because mainly resistor. If we increase the resistance, power factor will be better. Full load slip will be large because the characteristics will shift. So, but efficiency will be poor because there will be high I square R losses. This type of motors are used for appliances like punch press cranes, winches, etc. The starting current is reduced in motor with high reactance rotor, but they have low starting torque and low power factor. Because if we increase the reactance, the resistance will reduce, so power factor will reduce, torque will also reduce. Motor will double cage will have excellent starting condition with good speed regulation, good efficiency under running condition because they have high resistance at starting and low resistance at running. Double cage means we will see discussing the construction that they have got two rotor cages. So at starting, as the inductance effect is very predominant because of the high frequency, so the current will mainly flow through the outer cage, so resistance will be high. But when the motor is running, the slip becomes small, so frequency is small, so current distribution becomes more or less uniform. So both the cage will carry current, and so the effective resistance will reduce. So these motors have good performance. Now, for any motor, speed control is an important thing. Now, what happens? The induction motor is more or less a constant speed motor. Constant speed means not that speed remains exactly constant; it changes slightly with the load. Unless we have an elaborate speed control arrangement, the motor speed mainly depends on the load connected to it. So, and normally from no load to the full load, the speed drops very slightly. So characteristic is almost similar to a DC shunt motor. The speed dropping from no load to full load slightly. But one of the advantages of DC motor was that the speed can be very easily controlled in a very inexpensive ways. That is, that simply inserting resistance in the field and armature circuit, we can control the speed of the DC motor over a wide range. That is not possible in case of induction motor. Induction motor speed control requires a very complex, elaborate circuitry, and that is only possible with power electronic circuits. So, as you have not studied power electronics, so this portion will be dealt with in drives class. What I will just explain is the basic principle of speed control of induction motor. Now, what is the speed of an induction motor? By definition, the speed of the induction motor will be 1 minus s into ns, where ns is the synchronous speed. So, synchronous speed again is 120 f by p. So, if you look into this expression, so if you want to change the speed of the motor, so either it is possible if we can control sleep, or if we change sleep, or if we can change the synchronous speed. Now, if we want to change the synchronous speed, then either we have to change the frequency or change the number of poles of the stator connector. Now, so there are basic methods. First one is the voltage control. Now, the voltage, if you remember the torque expression, this is the torque expression. Now, here you can see that this was R Thevenin. R Thevenin is Xm by X1 is almost 1. So, approximately R1 plus X1. So, again, B Thevenin is also approximately equal to B1 because this ratio is almost 1. So, your torque expression, this torque expression, we can write as B supply voltage square R2 dash by S, R1 plus R2 dash by S plus X1 plus X2 dash square. So, if in this expression, this R2 dash for very small slip, R2 dash by S, this quantity is very large compared to both R1, normally all this stator resistance, and total X1 plus X2 dash. So, if we neglect this, so approximately your I2 dash will become S by this V by R2 dash by S. So, SV by R2 dash. So, your torque become approximately 3 by omega S, 3 V square by R2 dash. This is obviously an approximate expression. I have neglected the stator resistance and also neglected the inductance of the circuit. So if the slip is to be doubled, say if we have a constant torque, then if the slip is to be doubled, then we have to reduce the voltage V. So if we want to make S double, so voltage should be reduced by the ratio 1 by root 2. Now if we reduce the voltage by 1 by root 2 and the torque is the same, to remain the same, that can be only possible if the motor draws more current. So the corresponding current will be again increased by factor root 2. So the motor therefore tends to get overheated because it will draw more current. This method is not that very suitable method for speed control because we cannot overload the motor. So but it has a limited use. Basically, in the ceiling fan, what we control is the supply voltage. So in the fan, the advantage is that the torque is not constant. The torque is proportional to the speed square. So it's a non-linear characteristic. So the current does not increase proportionally. So and this is a very simple method without much complication in the circuit. So this voltage control used for controlling the speed of the ceiling fan. However, the ceiling fan, they are not three-phase induction motor, they are single-phase motor, but the basic principle of operation almost speed control operation is almost the same. Second method is the rotor resistance control. Now, rotor resistance control is only possible in case of slip ring motor. So when we have derived the expression of the torque, we have seen that the torque become maximum for a particular slip, and the slip at which the torque become maximum is directly proportional to the rotor resistance. But we have also seen that the starting torque, the maximum torque, the value of the maximum torque does not depend on the rotor resistance, that is constant. So the advantage is that if we can change the rotor resistance, the characteristics will shift like this. That is, as we increase the rotor resistance, the slip at which maximum torque occurs will increase. The characteristic will shift like this. So there is a value of the resistance for which we can have the maximum torque at starting. So if these are the four characteristics of the same motor with different values of rotor resistance, then if we consider a constant torque, load torque, then we can say that with different rotor resistance, the motor will run at different slips. So the speed will be different. But obviously, as we are inserting resistance in the circuit, so there will be large I square R losses, so efficiency will reduce. So these also have a very limited use for application, small motor application, where it is not advisable to use expensive speed control devices, and the speed range is very small, and the short time period of requirement is also very small. Then we can go for this method. But obviously, this is applicable for slip ring motor only. Say for example, consider a problem. Say there is a 440 volt, 50 hertz, 4-pole 3-phase delta connected motor. The leakage impedance of this is a stator resistance. This is the total reactance x1 plus x2, and this is the rotor resistance. This is per phase, ohms per phase. This is for delta connection. Motor is delta connected. So refer to the stator side. The stator to rotor voltage ratio is 2.5. Determine the external resistance to be inserted in the rotor circuit. so that the motor develops a gross torque of 150 Newton meter at a speed of 1250 RPM. So this is a 4-pole motor. So we have 50 hertz supply. So synchronous speed is 1500 RPM. So our sleep is 1500 minus 1250 by 1500, that is 0.167. And omega s, the synchronous speed in radian per second, is 157.1 radian per second. Now the total leakage impedance referred to the stator, this is for delta. So if we convert this to star, equivalent star, this will be 1/3 of this. So this is the impedance per in ohms per phase for star connected. Now let R2 dash be the new resistance of the rotor circuit. So this is equal to small r2 dash, that is the rotor circuit resistance plus the external resistance. So this is our torque expression. So in this expression we can put the value, the torque wanted to develop torque with 150 Newton meter, 3 by omega s, then V square per phase voltage will give 440 by root 3 square, R2 dash by S, R1 plus R2 dash by S plus X square. So putting the values, we can derive we get an expression of this. From here we get two values of R2 dash, 1.27 and 0.073. So this value is neglected because our R2 value is given as 0.083. So we cannot have a smaller value than that. So your total R2 dash is equal to 1.27 ohm. So external resistance R external dash, that is referred to the stator side, will be 1.27 minus 0.083 is equal to 1.19 ohm. So the actual value of the resistance which is connected to the rotor will be value of R external dash by the turns ratio square. So that is 0.19 ohm per phase. Now the one method of speed control which can be used for squirrel cage motor is pole changing. Now pole changing cannot be used for slip ring motor because slip ring motor we have poled winding on both stator and rotor, and both the winding should be connected for the same number of poles. But in squirrel cage motor we have an advantage. The stator winding is connected for a particular number of poles. The rotor, it is a bar winding, so it adjusts itself to the number of poles the stator has created. So if the terminals are available and the stator terminals can be reconnected into with some other number of poles, say then the rotor will get adjusted to the number of poles of the stator. Now, if we change the number of poles, that means the basic synchronous speed is changing. So we will shift to some other characteristic. So it is discrete, it is not continuous because discretely changing synchronous speed. So that and only possible for slip ring motor. Now it requires a detailed connection of the windings. If possible, I will discuss this pole changing during the after we have discussed the construction and the winding. Unless you understand how the windings are created, now it is not possible to explain the pole change. So we discuss the windings, the winding connection during this, construction. Then we can discuss the pole change. So this is the basic of study, and actually induction motor speed control is a very vast subject, and when you go for study drives you will study this because this all will require this power electronic circuitry, because we have seen that if we can change the frequency, synchronous speed will change. So frequency changing requires power electronic circuitry, and actually for induction motor, if you remember, neglecting the drops, your supply voltage is approximately equal to the induced EMF, and from that equation you can see that the flux is approximately proportional to V ratio V by M. So basically we cannot only change the frequency, we have to change the voltage also, keeping the V by F ratio constant, because the machine is designed for a particular flux, we cannot exceed that. So in all the cases we require complex electronic circuitry, so it is not possible to discuss here. But induction actually that cost of a DC machine of the, if we compare the cost of a DC machine and an induction machine of same rating, DC machine will cost more because it will require the commutator, brush assembly, and more copper, so it is costlier, and it also require more maintenance, because particularly compared to the squirrel cage motor, because it has a commutator and brush assembly. But the main advantage of DC motor was that its speed control was very effective, very easy, and very inexpensive. So initially in the industry, watt motors are mainly used as the DC motors, but nowadays actually we have very reliable power electronic devices. So with power electronic circuitry, we can control the speed of the induction motor very accurately. So it is DC machines are being replaced by induction motor. But still, though the motor itself, the induction motor itself is inexpensive compared to the DC motor, but the total combination, that the DC motor with its controller and induction motor with its controller, the induction motor with its controller is much more expensive and much more complex. So I will stop here today. We will go for construction in the next class. Okay. So next class I will take on next Tuesday. I will not take next Thursday because not much left of the syllabus. So next Tuesday